Hi everyone, welcome to my channel again. Today, as you can see on my screen, I want to show you how you can simulate a GNSS antenna, chip antenna. It's Global Navigation Satellite Systems antenna, and this chip antenna has a very compact size, so it's perfect for wearable devices, cell phones, and the frequency band is the upper L1 band that is used for GPS. And yeah, again, in automotives and the rest of applications I mentioned, you can use it to basically use GPS for navigation. So this antenna has a very simple structure. You can see a ceramic inside. It's kind of like enclosed by like two metallic, I think it's gold, AG, or is it AU? I'm not sure. Anyway, that looks like the two sides of a dipole. But it's, yeah, using the ceramic, which has a very high permittivity, they were able to basically um, make the size very compact, and then it made it perfect for embedded, basically to make it embedded in other boards, in a board with other applications like Bluetooth antenna, or like I don't know, anything else that you would need for any other component basically that you would need. And you can use this antenna with a GNSS module to basically receive signals. Okay, so the electrical specification is that this is ceramic, and the band is 1560 to 1610, 50 ohm. Return loss is minus 12 dB. Again, depending on your structure. The efficiency is 75% or minus 1.2 dB. And then the gain is 3 dBi, and the maximum RHCP gain is 1 dBi. So as you might know, GNSS is RHCP is in RHCP. So this is a linear polarized antenna. So if you use this antenna, you are naturally going to lose some gain because you're not capturing the whole RHCP signal. Okay. I'm not sure if this is showing this properly, but okay. So first thing we need to do, what you can do, obviously in your design, you might not stick with whatever suggestion this data sheet is making, but in order to simulate it and see if you can make it work, I would strongly suggest to start with basically what the datasheet is suggesting, right? The dimensions and structure and everything else. Okay, so since this is a PCB, a chip antenna that you can use in a PCB, and you know that PCBs usually have more than two layers or one layer, the first thing you might notice is that, okay, this is the structure it's suggesting. You have three pads here. Yeah, first of all, let's just start with that. You have a massive ground layer, okay? You have a massive ground layer, which is a coplanar waveguide kind of situation. As you can see here, it suggests that you would definitely use vias to make this ground a solid, like a solid ground, basically, by connecting it using vias to other ground layers, RF ground layers. Okay, so here's your feed line, and here's if you just look at my cursor here, here's your feed line, and here's the ground layer. Okay, and then the vias are just making sure that the ground stays ground. You have nothing basically disturbing this ground, especially in a PCB design. You would definitely have crosstalk or something else that might disturb this, right? And then you have three pads. One of them is to contact your ground layer, and then the other two, one of them is to feed it, and the other one is to create a return path for the antenna. Okay, and then what else we have here? And then you have suggestions for these pads. Something else that is very critical is the size of this ground clearance, okay? So on the first layer, you would have definitely this ground clearance layer, and then it says pad dimensions on PWB layout, and then here, you see in red, it says ground clearance area. This ground clearance, this rectangle, okay, it should be removed from all layers, okay? So you're not going to have a ground clearance on the like a main layer that the antenna is on, but other layers as well, just so that like the antenna is not disturbed, especially that you might guess in this antenna you would have a considerable back lobe radiation. So if you place any kind of like ground layer, battery that is very metallic, or anything else beneath this antenna, because your wearable device dictates that, you're going to disturb the pattern, and then naturally you will disturb the S11. Okay, so these are very general knowledge about this, going through this data sheet of this antenna. And then here it is. It says the S11, which looks like a perfect one, minus 30 dB, on a 80 by 37 millimeter test port, okay, without matching circuit. So so we can do this. We can try to see if we can replicate these results, okay? Well, I don't want to exactly replicate it, because it would definitely involve some feed line, optimization, which is not the focus of this simulation. You can play or like parameterize that to make it a perfect S11. But I just want to go through like what you would need to set up in Ansys to simulate this structure. Okay, so let's go by, so these are the ground layer structures, and then you have the antenna side as well. I think I found the antenna structure, then antenna structure from somewhere else. So I'm going to this antenna thing. So I'm going to copy it here. I think you can either request it or try to find it online and download it. Okay, so let's just say we have the structure of the antenna, or you can try to make it yourself. It's not like, let's see. Okay, so this is the antenna itself, right? So for example, how can you try to make this? First of all, the compact size is like here. So this is 2 millimeter probably by 10 millimeter by 3.2. You can try to measure here edge. Let's see. So this is 9.8. So I'm thinking that these are 0.1 millimeters thicknesses to make the whole thick 10 millimeter. And then the rest of it you can measure as well. And once you get there, if I'm not mistaken, you can see the pads, the bottom pads here, and then the upper pad, like this distance obviously matters. I'm not sure if they would disclose that, but like, again, you can try to make a guess, make your own chip antenna design basically. But it has a very simple design. Okay, then what we can do is you can press on O, the short circuit O, and then that would allow you to, on your keyboard, and that would allow you to basically choose objects. And here, you can see I already assigned materials to the ceramic. This is a material I made myself, okay? If I want to show you, you can say assign material. You might have seen this in my other videos, but in HFSS, you can add a material yourself. For example, add a material, you can say ceramic, let's say 2, and then I use actually ChatGPT to tell me what is a normal, like a typical ceramic properties, electrical properties. Like you have from 30 to 45 a relative permittivity, and then something like I don't know, 0.002 dielectric loss tangent. So you see, you come here, you can say ceramic 2, and then relative permittivity is, let's say, 35. You can have different ceramics, right? And then permeability is 1 because this is a non-magnetic material, and then loss tangent here, dielectric 1, you would put 0.002. Okay, and then you just save it. You can put 1 gigahertz, like, I don't know, again, you can try to dictate these properties um, in different frequencies, but you can say at 1 gigahertz, these are the typical electrical properties of my material, right? You can even I make it more interesting. Or no, actually, I make it in another video. But you can say even tensor or anisotropic, then that would allow you to have like different properties in different axes. For people who design metasurfaces, this is really interesting because you barely have materials that are homogeneous, and then they have like the same relative property relative permittivity in all directions. Or if you design Huygens metasurfaces, definitely you would anisotropy, right? So you can dictate that, and then, or tensor. For tensors, you can even like, yeah, you can just not make it not symmetric and then go crazy with this material. I think there was something that you would allow you to even, if I'm not mistaken, nonlinear, yeah. So you can even like, import data here to show how the permittivity is nonlinear, because as you know, the permittivity can change with frequency, right? So if your simulation is very wideband and you have a known material that is like super nonlinear, right? You can even like import that and see like how the properties or how the antenna or your RF device change well, S11 or whatever changes with the permittivity, nonlinear permittivity of that material. Anyway, so that's how you can do this. Was a very long explanation on like how you can define different materials here. Again, mostly for people who are designing like um, electromagnetic materials, that these things would be interesting. But anyway, so let's go to 40. Okay, I'm gonna use the design, the material that I designed before, and you can just, yeah, you can just assign this. So press OK and then assign it. Then for this one, if you can assign PEC, just again, PEC is a material that is, I didn't make it. It was already in the project, so you can assign PEC, because if you don't assign material to an object, it will give you error. So, but then what else? Something else you can do so that this doesn't go into a complicated simulation, and you just want to quickly go through your simulation, especially for the first rounds when you're just optimizing from a very educated guess, let's say, on the dimensions of your microstrip line, or like, let's say, feed line, let's say, right? Or what should be the thickness of your substrate. So very quick simulations on like going to the converging to the first initial optimum solution. You don't want to like solve these as like objects. What you can do is come here, assign boundary, and then you assign perfect E to it. And the same thing. You can either assign perfect E. Well, these already came, so I'm gonna delete these, or choose both of these together. Actually, I have it. Control and then pick the other one, and then just assign one perfect E to both of them. So yeah, now this showed up, right? This is ceramic, this is perfect E. Now what it does is that it's going to just solve the solution on the surface of these metallizations, doesn't go through inside that 0.1 millimeter thickness, and then it's going to make your simulation way faster. Okay, so this is the antenna material, super easy. Now with this antenna, it's not actually the antenna that is hard to design. It's the ground layer that you would have trouble, basically. So let's go with this 80 multiplied by 37. Okay, so I'm going to quickly draw. Where am I? Okay, modeler. No, draw. Oh, there are. Here. I'm like, where is that? Okay. So again, if your PCB, you know that you would end up changing the board size, I would say parameterize everything. Parameterize the ground clearance, the pads. Well, not the pads, because the pads are pretty well defined, and like I don't think you would want to change those. But the ground clearance, everything, so that like when you change one dimension, your whole structure doesn't change. You know, because sometimes you can have this case that you don't parameterize, you change one thing, and then because Ansys doesn't show you the updated, if you use basically if you change the dimensions with the this what do you call it, parametric analysis, it doesn't update your model, right? It doesn't update your model, and what happens is that you won't see how your structure looks like, so you wouldn't notice that your antenna is not connected to anything basically, or your structure is completely wrong and have a discontinuity now. So when you parameterize, everything gets updated together, things stay together, and that's better. Anyway, so let's just start. So I'm gonna make it quickly a ground layer, and then come here. You probably know these stuff, so I'll just do these things very quickly. Let's say this is the first layer, H, and then so W is, let's say, 37 millimeter. That's our X. So actually, no, it's the other dimension. So 80 millimeter. And then L is actually, maybe I should have named them the other way around, but it's fine. 37 millimeter. And then somehow we have H defined. H is the thickness of our substrate. So that's the top layer for me. So here, I think I already have this guy, the antenna, if I'm not wrong. Somewhere H is defined here. Yeah, definitely. So yeah, you can start by 0, putting this guy in the center, but because I copied it from another design, all you do is that you take this guy and then define a parameterized move. You move it with parameters. Oh my God, parameters. Okay. So we have this one, right? Now it's we have to define our ground clearance. Okay. Now let's say I have 2 layers, okay? Because I want to show you how the ground clearance thing works. So we have 2 layers, and then let's do that. So I'm going to copy this guy, make it Control V, and then what I do here, I put this one on 0. So this is my bottom layer. Now you can see 2 things. And then, you know what I really don't like is this grid, but not grid here, but it's fine. Okay, so you see I have 2 layers now, okay? Now, I don't want to assign the PCB yet. I want to go ahead with the ground clear, PEC, not PCB, PEC. So now let's define the ground clearance. Okay, the ground clearance is how can we measure that? So we have this one in the x-axis, which is our longer axis, 10.8. Okay, so I'm going to call this minus WG, ground clearance, or GC, over 2, minus LGC over 2. But remember, this antenna is placed actually on the edge of this PCB. So we have to, on the y-axis, you have to say L over 2, and then minus blah, and then this is the top layer ground clearance. I'm going to, WGC is 10.8 millimeter, and then LGC is, let's see, 6.25. You see, from here to here. So read that very carefully, okay? Then WGC, and then LGC. I think I actually made a mistake, but I'll tell you what. I'll show you. I show you why I made a mistake. Now it's gonna get centered on the edge, but let's see. So I apply it. You see, this ground clearance got centered on the edge. What you can do is like just remove the initial one, so it goes from minus L to plus. Now, if I update it, it's gonna be this. Okay, let's see. Okay, it's coming together. Now we want the same ground clearance in the other layer. So again, I copy it, I make it the Z to be 0. So that's our bottom layer. And then what I do is that on the first one, I subtract the ground clearance. I really don't know how. Okay, operations here. Because I made this smaller, it's a little bit tricky for me. So this is right. And then rectangle 2 minus this, subtract. Okay, so now we have our ground clearance, okay? Then we can choose a substrate here as well. So let's put our substrate between the two layers, okay? Again, the same length, minus W over 2 minus L over 2 from 0. This is L, this is W, and then this is H. You have to see, H is 1 millimeter, it's set to 1 millimeter, okay? So again, you have the choice, you can just make it anything. This is, if it's 1 millimeter, it would be a very thick PCB, but like this is just for education, so it's not very realistic. Okay, so again, for fast ones, I strongly recommend you keep these as sheets, and then you can assign PEC to them, or we can continue with the pads and then we do that. So now let's show it from the top, okay? Let's go to the pads. From the top, sorry. We have, let's just start with this big number 3 pad, okay? Number 3 pad. Okay, so I'm gonna call this pad 3, so I would remember which pad this is. And while I'm at it, I might as well change the name of these layers. Layer, top. This is just making sure this is the 0 one, the bottom one, yeah. So this is layer bottom. And then, you know, if you want to get very realistic with this, you can just keep adding more layers, but usually after 3 layers, especially if the bottom one is complete ground, RF ground, then it doesn't make any difference. Okay, then pad 3. Okay, for pad 3, let's see what we have here. I'm going to zoom in here. So for pad 3, before, these are very tiny. Okay, so we have a little bit of 0.4 millimeter till top 3 is, sorry, pad 3 starts from the edge. So that's our offset from x-axis, right? sorry, from y-axis. So 0.4, I'm gonna add, how can we, first of all, on X side, it starts from the ground clearance, right? So WGC, let's go with we want to put pad 3 on the left side. Okay, so that would be minus WGC over 2. Then we have L. You can, if you know what you're doing, honestly, just skip through these parts. It's the painful part. But then we have L, which is the edge of our board, L over 2, right? Minus 0.4 millimeters, right? And then I'm going to design this way reverse. I'm gonna just start from L over 2, which is the edge of my board, then minus 0.4 millimeter, because that's right here, this edge, right? And then I'm going to put H here. We'll see what happens. It's not the end of the world if you get it wrong. Then for the X size, it's going to be the pad size here, the pad 3 size length. So pad 3, or let's call it W, because I stuck with like P3. Then yeah, it's going to be plus, because we started from the left side, we are going to the plus side, WP3. And then here, it's going to ask, what is WP3? WP3 is 1.7 millimeter, if I'm not wrong. Yes, 1.7 millimeter. So we are going to put 1.7 here. And then for the Y size, we started from this edge. This edge, we have to go all the way in, which is like the negative side, minus LP3. LP3 is 3.2 millimeter. You see here, 3.2. So be careful about the negative. Don't double negative it. Don't double negative it. Anyway, okay, so we got it. We got it, guys. We got it. So we have, did I put H? Yes. So immediately what we can do is add top layer to this guy. And I would suggest to keep united and then keep the same. First choose the layer top, because if you add them, unite them, then and choose pad 3 first, then it's going to rename your whole structure to pad 3. So I don't like that. Anyway, so we got this one, right? Okay, perfect. Now let's go to the other one. I know it's painful, so skip through it, but I need to make these. So pad 2, let's go pad 2. Pad 2 is again the same thing. So we are going to, this time we are going to start from the right side. So WGC over 2, and then L over 2 minus 0.4 millimeter, and then H. And X size is, you can use WP2, but they're the same, but in case like WP2, because we are starting from the right, this pad goes inside, so it's the negative side, and then WP2 is also 1.7 millimeter, and then the other one, again, minus LP2, that one is 1.45 millimeter. Let's see how it looks like now. If I get it right, I'll be very proud. Perfect. Pad 2. Okay, got it. So now we add this and this. Now we are going to go. Honestly, it would be nice to save this project at this point, but then my risk tolerance is high. Okay, so let's go WGC over 2, and then L. What was I doing? Okay, now again we are at the positive side of this, so L over 2, then minus 0.4 millimeter. Then we have something else. We want to get to this edge of pad 1, right? You see it? So we have 0.4 from here because pad 2 has it. Then we have pad 2 length, so we have to add minus LP2, right? And then we have 0.4 millimeter, I said it, 0.4 LP2, And then we have this little thing going on here, which is we have to calculate it, because from here, what is it? 1.45.4, and then I'm trying to calculate the distance here. So we have 3.2 minus, I'm guessing 2.9. Yeah, 3.2 minus 2.9, because we have 1.45 for this, pad 2, 1.45 for this, 2.9, 3.2 minus, that is going to be minus 3.3 millimeter. If you didn't get it, just look at it a little bit. You will get it, H here. Okay, then, or maybe I'm mistaken, but let's see. Then we have WP1, which is, again, 1.7 millimeter. And I think I should have put negative because we are coming from right to left. Then, oops, no, don't do that to me. Minus, and then here we have minus LP1, which is again 1.45 millimeters. So I kept the pad size just for the fun of it, Yay, we got it right. Okay, so now we have layer top plus this guy. That's our, guys, that's our top layer. Okay, I made a mistake, because pad 1 actually is not connected to the top layer. So we are gonna go, I made a mistake. Pad 1 is actually going to be connected to the feed line. So it's not part of the top layer. So now we can go assign boundary, PEC. Okay, bottom layer. Where is my bottom layer? Bottom layer, again, PEC. Good. Okay. Then what else do we have? Okay. So now we have to design this pad and the feed line. Okay. So for the feed line, at this point, I'm gonna just save this. GNSS, Ansys. Okay. So now, good. I have, okay, so something we can do is to just draw the pad, honestly, the microstrip line, but then it would be, you can't change anything, right? So what I'm going to do is just create an arc here and then bring it to the line here. And because design of the feed line is a whole thing on its own. I'm not going to design a feed line for this antenna. I just want to show you how to simulate it very quickly. So let's do it this way. I'm going to create a circle. The center is going to be here, and then I'll show you what I'm doing very quickly. So the center is actually going to be, again, parameterize everything. So XY is W GC over 2. L, the center is L over 2, the edge, and then H, the top layer. And then what we have here, the radius is actually 0.4 millimeter, if you remember, 0.4 millimeter plus LP2 plus that 0.3 millimeter. And I'll show you what happens now. So we have this, okay? Yeah. Then I'm going to create another circle. Oh, no, that's not a circle. Escape. I'm going to add another circle here. Or, you know what? What you can do is just copy this. And then we just change the radius. 0.3 plus LP1. Either LP1, or you can just say, let's design a microstrip line by itself. So it's going to be plus, I actually have a better idea. I'm going to microstrip line or feed line, let's say feed, WF, right? I'll show you how. So the center of the feed is going to be here, and then we have WF going minus, and then WF over 2 plus. So the center is going to be LP2 plus. So we got 0.4 from the edge, then LP2, then 0.3, then we need half of the length of that first pad, P1 over 2 plus WF2. And then WF is the width of our, let's say, macro strip line. So it's going to be like, let's say 1 millimeter. Okay. Again, I haven't optimized anything. And then circle 1, I'm going to change it about circle 1 to 0.3 plus LP1 over 2 minus WF. WF. Apply it. Okay. Now let's see what happens. So circle 1 minus circle 2, that is going to leave me the feed, okay? And then I only need like literally quarter of this. So one very bad way to do this is just, you should parameterize these, okay? I want to quickly do it quickly, basically. So we are going to go circle 2 minus these two, minus these two rectangles to be left with the only a quarter. I don't know if you have a better, what did I do? Did I put this in H? Remember, they all have to be in H. Oh, I think my circle is not on H layer. The top layer. It has to be on the top layer. This is H as well. And then circle 1. No, this is H. Did I do it? Yeah, I must have done it to the other one too. Operation, subtract. Okay, left with this. Now top layer minus, or we leave, sorry, pad 1 plus this feed line is going to be our feed line, basically. Unite. This is our feed line. Then what we need is a clearance from here. So you can define, again, a gap, or you can just go by the size of this here, right? Stick it to the pad 2. So we can do this as well. This is becoming very long video. It wasn't my intention at all. So I'm gonna go back here actually. I'm gonna keep these two pads because I'm gonna need them in a second. So I'm going to make another one, another circle here, one here, and then another circle here. I'm gonna make everything. Again, not the best way to design this, but not too bad either. So circle 3 is going to be connected to pad 2. So WGC over 2, L over 2, and then H. And then here we have, what do we have? The radius is 0.4 millimeter plus LP2. Let's see. Okay. Again, not the best way. You want a bigger ground here, but like, let's do this. So minus circle 1, minus circle 2, actually, circle 3. You'll see in a second what happens. Minus circle 3. Oops, what did I do? Oh, I see what I did. So we are going to actually remove pad layer top. I'm going to remove this pad from it and then layer top. Okay, first remove the circle 3 here and then add the pad to it. Subtract, subtract. Okay, then I'm sorry, I don't know. 1 second. Okay, so I see what I'm doing. So then You can definitely fast forward these parts. You can go ahead with your design. So circle 3 minus circle 5, or sorry, the other way. Circle 5, circle 3, and then subtract. Okay, and then layer top minus circle 5. It's messy, I know. It's gonna clear up in 1 second. So, okay, so we got this one. Then this is our microstrip line minus these two, subtract. Okay, this is our pad. This is summation. Okay, and then things are coming together, guys. No, not really. They're not coming together because I think my circle 5 is still 2 plus WF 2. Okay. For 1 second, we're going to remove this guy. Okay, not bad. It's coming. Okay, so now we add the top layer and then rectangle 5 together. This is hard, guys. Okay, so this is our feed line. We still have to remove the other side of it, so let's go. I'm gonna make the other one and then just bring it, okay? Okay, I did the other side, but something, before I perfect this, basically, something else came up that I thought like it's nice to know, okay? So what I'm going, my top layer has this part left, which I don't want to include because that's the feed line, right? So what you can do is press F, choose this, and then edit it, and then go to surface and you say create object from this, right? And then what I'm going to say is top layer minus this object. That would remove that one for me. So I don't actually have to, voila, you see, like, that's nice. Okay, so now we have, I don't know why do I have this one, circle 2, where is circle 2? Okay, this is another PEC, perfect E. The top layer is also PEC, so everything is working now. Perfect. Oh, now what we need is a boundary condition. No, sorry, the radiation box. So I'm gonna control A here. Control A. Are you gonna control A or what? So this is our top layer. Oh yeah, you have to go to object, press O to control A, and then we are going to add. No, don't. Create a pad all directions similarly, and then region. Then what we need is you can, oh, we didn't assign any material to this. So you can assign any material, like let's say FR4. Usually you don't need, you're not going to use FR4 because it has a lot of loss. But anyway, I'm just going to use any material for now. Okay, that's not the focus. Then what we need is a boundary condition. So what? Control A. Pad all directions similarly. 1 second. So the next thing we need is the radiation box, which is, I'm going to say transverse padding, transverse padding, and then add this, and then I'll add the radiation boundary to this, radiation, okay, and then bring it here, So that's our radiation box. Now, if you want to simulate this, the first thing is going to tell you I don't have excitation, right? So for excitation, something I noticed Ansys has done is a very nice change actually, because now you don't need to put the wave port at the edge. It actually suggests that if it's not at the edge of the radiation box, it will allow you to basically put a like a PEC box on the back to just create that if the same effect. So now what we need is I'm going to rotate this. Okay, so we need the same. Since we are done with this, I'm going to maximize this size so I can see what I'm doing. Okay, first of all, grid off, and then grid. And then what we need is a wave port that goes from, I'm going to make this go away too, and that covers the macro strip line and the ground. So what we can do is, and that would be in XZ plane. So we have to change this to XZ and then create this box. Okay, and this is going to go to the y-axis is going to be L/2, the edge of the board. And then the rest of it, let's see, the rest of it is, let's say this starts from WGC, the positive side, GC/2. Then on the other side, we go from 0. This is H. And then the length of this one has to be more than 3.2, let's say. 3.2, is it 3.2? I think 3.2 millimeter. Just to cover from one side to the other. Let's see. No, not enough. Okay, so we can just say L wave port, like 6 millimeter or something. Okay, and then we can actually, the wave port can start from below that, so minus H multiplied by 3H. So we'll cover all of it. See, now we choose this guy and then say assign excitation, and then port is, you can model wave port, and then integration line, you can go from one edge of the macro strip line to the ground, and then to the ground, and then we do not normalize this. Thickness. Okay, now this is the PC backing, because we are inside the radiation pattern, right? Cover holds. Okay, so now everything I think is good. Just make sure if the PC backing comes inside, you can flip side it, right? So you can do that as well. Now I think we should be good. Let's see. If you go to simulation, let's validate this thing. So analysis setup. What does? Oh, well, we didn't add any analysis, so we can do this. Add solution. I don't like the auto, so this is, let's say 1.5 gigahertz, and then maximum number is 20. Make sure you definitely have like 3 conversions, and the minimum is like, let's say 7, just to make sure everything is okay and you're not getting a basically random convergence. And then remember our frequency was 1560 megahertz to 1610. So let's start from 500 to 700 megahertz, and then this is megahertz as well. And then this is, we don't need 101. Like, let's say, first, let's do 21 points interpolation. And then something I missed is that 1560, that would be, I think, 1.5580. That's, yeah, 50. This is the central frequency. So we want to put the setup in the central frequency and then go do that. Now, if I like simulate this, it probably not going to just, it's not going to, oops, what am I doing? It's not going to work, but I mean, S11 is not going to work, but I'm going to show you what are the things you can look in. Okay, just 1 second. Yeah, I was just Googling this part. Okay, to make sure I say it right. Okay, so 5 passes, 6 passes, and then you can come to results, solution data, and then look at the convergence here. So it hasn't converged yet, and we need 3 convergence. So let's see how many it takes. You can either table it or plot it here, you see. That's why I say do more than 3, because if you got here, it would actually say, if you just put the target of convergence to 1, it would just stop here, right? So that's why 3 is the better version. So just do 3. So that, like, yeah, you don't get random convergence. Okay, and then now it's going to work on the frequencies. It converged. Where is it? Convergence or table. It worked. It converged after 12 passes, basically. And now what you can do here, you can look at the S11. I doubt that it will work, but let's see. Okay, not bad. You can optimize this thing, like first trial, not bad. At least we got at least we got a minimum here. Then what I'm interested in is to look at the far fields. Oh, where is my far fields? You can say insert far field setup, infinite sphere, and then theta, I usually put it from -80 to +80, so I can get like the whole thing. No, actually that's, yeah, no, that's correct. You go from 0 to 180. That's okay. Then what we can do is just go to far fields now. And remember, far field like is a post-processing thing. So if you miss it before the simulation, it's fine. Now we can do 3D polar plot and then gain total and then dB and new report. And then what we can do is just voila, like look at this. It's beautiful. Show in modeler. And then we come here and then you can do this and look at it, right? This is the radiation pattern. You can even compare it to the data sheet. It's pretty beautiful. It's pretty close. Like, where is the radiation pattern? Should have a radiation pattern. Yeah, you see, like, this is the other version. Like, it's from that side. And make sure the scales are okay. I don't know if this is a dB scale or not, but yeah, you can plot this, and then you can even, like, this is at 1580, obviously, the radiation pattern. If you want to add more, you can do the same. You can do this, like add solution setup, and then, sorry, you can come here and then add another frequency sweep here, and then say 1560 to 1610, for example, and then every 10 megahertz, let's say. And actually, let me just do this, like, I don't know, 1560, 1570, 80, 90, 10, and then 1610. So that would be 6 points, right? And then you have to put discrete here and then say save fields so you can get the radiation pattern in all of them and then analyze this. If you analyze it, then you would go here, let this finish basically, obviously, and then you come here, far fields, far fields, 3D polar plot, or we can even do, like, let's say radiation pattern, and you come here, sweep 1 and infinite sphere, theta, and the phi is going to be, right? Yeah, you can choose phi to be, which plane is this? Let me show you. This is XZ plane, for example, let's say, right? In XZ plane, this is this one. So actually, this is a phi rotation. Phi is rotating. Theta is 90 degree. Think about it, okay? Then we get it. Then the frequencies, we can choose all of them. New report, and let's see. Oh, I didn't choose dB. You have to choose dB, otherwise it looks ridiculous like this. So you see, not too bad. Yeah, not too bad. You can do the same thing for the other planes. And then obviously, yeah, you can do other stuff too. Like, for example, let's do this one, far field rectangular plot, and I'm going to show you the gain, total gain, and then for example, directivity. There should be a realized gain too. Gain, where is the realized gain? Oh, here. Gain, directivity, realized gain. Okay, let's do realized gain. What's the difference between realized gain? I'm going to add it for frequency. So we are going to come sweep 1 and then frequency, and then let's say the maximum, like on the phi 0, sorry, theta is 0, and then phi is 0 as well, let's say. Okay, the top point. And then realized gain, new report. Let's see how it looks. This is the realized gain. And then I'm going to add the total directivity on it. Sorry, I should have added. So this is this one, and then realized gain, add trace. And then the gain is going to be here, add trace. So what is the difference between these? Realized gain, you see it's way below here compared to the gain and the directivity. Gain and directivity, Ansys basically just deducts. It's going to calculate gain based on the delivered power, not the transmitted power, right? Because if the S11 is really bad, right, you have a lot of reflection, that means that your delivered power is going to be way less than the transmitted power. A lot of it gets reflected. So that's why the realized gain, which is the maximum gain over blah blah to the transmitted gain, it's going to be way less because it has the reflection loss in it too. But the gain is calculated based on the delivered gain. So that's why it's very close to the directivity, because it usually just takes into account the loss tangent that we added to the dielectric in that frequency. Or if you want, you even can make this better, add ohmic loss to it. For example, actually, let me go through that as well. Now this video has become super long, so let me just show that as well, that you can just come here. I'm gonna which one was it? This one. I'm going to remove this one, okay? Let's say we want to make this more realistic. As soon as you do that, you lose your solution. So I'm going to copy it and then do another one. So in case we want to come back, paste it. So just I want to mention that S11 that we have is not perfect. You should go through the parametric analysis of making that microstrip line better matched, right? Like you would go calculate, I don't know, use some online calculator to see what should be for a 50 ohm microstrip line with this substrate on thickness of 1 millimeter, what should be the length of it, what should be the gap, and then make this microstrip line better. You might have to increase the length, so make the port go away and stuff like that. But now I want to show you something else. So for your microstrip line optimization, that setup is perfect, right? But let's say you got to the end of your optimization. Now you want to consider ohmic losses and everything. These sheets, you have to basically add thickness to them. So you would come here, edit, and then say surface, and then you can say thicken sheet. And usually like you have 18 micron, 36 micron, basically copper deposits. So you can say like 18 micron here, for example, you would add that. And then that would come, you have to make sure that would come, it should be added on the other side out of the substrate, you see. So make sure that that is on the right direction. If it's not, then you would add, you can say both sides or the other side, put a negative one, things like that. And then add, what did I do? Okay, yeah, then you would add here assign material like copper, for example. Then copper has conductivity and everything in it, and then you can account for that, right? So you can even see the effect of the board size and everything. And then you can do the same thing to the microstrip line and make it more and more realistic. Remember that since we added thickness now, we have to bring our antenna up a little bit. So you can come here and then add, actually, it would be nicer to do this, let's say HC. HC is 18 micron, and then add it. And then add this one to it, so that now your antenna doesn't go into your the copper thickness, basically. Do the same thing to these guys as well. Just edit it plus HC. Oops. Got it? Okay. Now, obviously, this board will be filled with other components and stuff like that. I'm gonna do the same on the other side. Let's say this is a two-layer PCB. We want to make this copper is we want to make it thick as well, and then you can say both sides, or I want to add it to actually minus HC, and then do this as nan, and then you would see. You see, because it's the other direction, just to make sure that it's not going inside your substrate, because we are obsessed with details here. You see, this is, yeah, perfect. Now you have it. Okay, guys, I thank you for your attention. I know it was super long, but then it had stuff in it. So I hope that you learned something. I'm going to put this one here just to make it the thumbnail for the video.